Howdy. The purpose of this video is to introduce phase diagrams and some of the information that they represent. Now, phase diagrams are one of the most widely and most informative tools in all of material science, and they contain a vast amount of knowledge. So we're not going to be able to go into full detail, but hopefully by the end of this video, you'll be able to understand how to read basic phase diagrams, how to understand what phases are present, what are the compositions of those phases, what are the relative concentrations of different phases, and some information about melting and solidification in the phase diagram. Now, this is a very complicated system I've decided to show you at the beginning, just to scare you a little bit. You see a whole bunch of different phases present, a whole bunch of different fields with multiple phases present. We're going to start with something a little bit simpler, and this is called an isomorphous binary phase diagram. Isomorphous means there's a continuous solid solution, and that means that from one end to the other, at low temperatures, we have a single phase present. Binary is just referring to the fact that there are two components in the system. So this is an isomorphous binary phase diagram. Okay, the first thing we need to talk about is what's a phase, right? A phase is a form of matter that has distinct properties from other phases in the system. One definition is that you can consider on some scale chemically separating it out from other phases. Two different phases could have the same composition. So one perfect example of that is ice and liquid water. They both are H2O. They're both composed of the same molecules, yet one has a crystalline structure, that's ice, and one is a liquid. So those are different phases. They could have different compositions. So if we look at this picture in the middle, this is a granite. In granite, you have at least 4 different phases. You have a pink kind of a feldspar. You have a milky white. This is a different kind of a feldspar. You have this grayish color, that's quartz. And you have these little black flecks. Those are biotite. So these all have 4 different chemical compositions, and their crystal structure is also different. Again, each one of those has its own unique set of properties. So, for example, the thermal conductivity of quartz is different from the thermal conductivity of feldspar. Finally, we could have materials that have the same composition. They're both solids, they're both crystalline solids even, but they're different phases. And so one example of this is graphite, what is contained in a pencil, versus diamond. Both of these are pure carbon. They're both solids, they're both crystalline solids, but the crystal structure is very different, and that leads to the drastically different material properties, right? So graphite is black, it's very soft. Diamond is clear and very hard. This is because they have different crystal structures, different properties, so they're different phases. Okay, we've talked about phases. What about components? So a lot of these will just sort of arbitrarily say component A and component B. But what do we mean? We're talking typically about chemical components. So this could be an atom, for example. So one case could be if I look at gold and nickel, and I look at the phase diagram of gold and nickel. And so all of these phases would contain only those 2 chemical constituents. Composition, the components could be more than just a single atom, though. So, for example, I could look at the SiO2 Al2O3 phase diagram. In this case, I'm looking at this chemical unit, SiO2 unit, and this unit, Al2O3 unit. All of the compositions in the middle are some mixture of SiO2 and Al2O3. So oftentimes, we like to break it down as simply as possible. So you'll either see atomic components or some sort of simple molecular compound. So oftentimes oxides are broken down into their individual oxide components. So when you think about component, think about chemical constituents. So again, in this case of quartz, in this case of granite, the main components would be SiO2, Al2O3, Fe2O3, MgO, calcium oxide, sodium oxide, potassium oxide, titanium oxide, Geological systems are very exciting because there are usually many, many, many components in them. I could keep going on and on to some lower concentrations, but you get the picture. In this case, the chemical components are, there are quite a few components, and that's why we end up with a number of different phases in that system. Okay, what phases are present? So if I look at the phase diagram, I'm plotting temperature on the vertical axis and composition on the horizontal axis. I would say most of the phase diagrams you're going to encounter in material science use composition and temperature. That's not to say those are the only phase diagrams out there. I could think about pressure. I could think about other conditions on the vertical axis. How do I read what phases are present? I would consider a system. And so by a system, think about a closed box, and it has some overall composition. And this composition is a mixture of whatever components are present in the system. So this is the composition of the system. I could say at some temperature T1, what phases are present? So to do that, I draw a vertical line on the composition of the system, a horizontal line on the temperature of the system, and I say, what region am I in? In this case, I'm in a single phase region. This whole area, the area under this curve, is a single phase region where the only phase that's present is this alpha phase. So in this case, at this temperature and at this composition, the only phase present is alpha. What about if I heat it up? If I heat it up enough, so I'm way up here, let's call this T2, I'm in a different region. This is the liquid region. So again, there's only one phase present, and that phase is liquid. So I've heated up enough, the whole system is melted. What about if I'm in something like this? This is a two-phase region. So if I said, what phases are present at temperature 3, let's give this a different color, at temperature 3, at this composition, I come up, I find the intersection, and that is in this two-phase region. And so there are both liquid and solid present under those conditions. What are the compositions of the phases present? Remember, I'm showing composition on the horizontal axis. So in order to determine composition of phases, basically I'm going to drop down and read that value off the horizontal axis. Now if I go back to our T1 case, this is pretty straightforward. I only have one phase, and the composition of that phase is the composition of the overall system. And this makes sense, right? If there's only one phase in the system, the composition of that phase has to match the composition of the overall system. Same thing would happen if I'm up here in the liquid. Again, I'm in a one-phase region, so the composition of that phase is the composition of the overall system. But it gets interesting when we look at points that are in two-phase regions. So if I'm in a two-phase region, the first thing I want you to do is draw a horizontal line from one phase boundary to the other phase boundary. This is what we call a tie line. Anytime you're in a two-phase region, the first thing you should do is draw this tie line. Because what this does is it tells us the composition of those two phases that are in equilibrium at that temperature. So the tie line intersects the solidest over here. So the composition of the solid is given by this value. The tie line intersects the liquidus over here. The composition of the liquid is given by this value. What are the concentrations? Now, concentrations is different from compositions. When I say compositions, I mean how much SiO2 and how much Al2O3 is present in an individual phase. So for example, maybe this quartz is 99% SiO2, and maybe the feldspar is only 50% SiO2. What are the compositions of the individual phases? When we talk about concentrations, we're talking about how much of one phase relative to another phase is there. So for example, this granite has maybe about 25% quartz, about 50% feldspar, and maybe about 10% of this biotite. And the remaining percent would be the other kind of feldspar in there. So concentrations is how much of the different phases are present. And we can figure this out by a mass balance calculation. So again, we're going to say we have some composition of the system, and we're going to put ourselves in this T3 case again. So again, I'm in the two-phase region. I want to draw a tie line. Now, what I'm going to do is I'm going to break this tie line up into different components. We'll call this one B. We'll call this one A. And we'll call this one C. And so the way to figure out what concentration of phase at present is called using the lever rule. And so essentially, the amount of liquid that's present in this case is given by A over C, where A is the length from here to here. The amount of solid is given by B over C. So B is the length from here to here. And we're going to talk about the lever rule in more detail in a later video. But to figure out concentrations of phases present, we apply the lever rule. Okay, finally, melting solidification temperatures. This, again, comes back to these phase boundaries. Sorry. The solidus and the liquidus. So the solidus is the phase boundary that separates a solid from a solid plus liquid system. The liquidus separates the liquid from a solid plus liquid system. Another way to think about this is the solidus is the temperature at which a material will start to melt. So if I have my system composition here, I heat it up at this temperature, that material will start to melt. It will continue melting over a range of temperature, and when it intersects the solidus, it is entirely molten, so it's entirely liquid. The other way to think about that is when you're cooling down. If I start off with a pure liquid, a material will start to crystallize or start to solidify when it hits the liquidus. So that's the definition of the liquidus and the solidus. We're gonna pass on the example problems for now. Come back to this. All of the things that I showed you on that simple binary isomorphous diagram are perfectly applicable to more complicated diagrams. So if I were to pick some system composition and some temperature, I could come over here, come up here. This is a two-phase region. It's L plus epsilon 2. I could draw my tie line. I could give you the composition of the liquid, X sub L. I could give you the composition of phase epsilon 2. And I could figure out how much of those two phases are present by applying the lever rule. So again, I would look at A, B, C, and look at the ratio A over C and B over C. And that's going to give us the concentration of epsilon 2 phase and concentration of liquid phase, respectively. Finally, I could say, the liquidus for this composition is here. The liquidus for this composition is here. The solidus for this composition is here.